Chapter 7 of the Chemistry of Cookery by W. Mattieu Williams. This LibriVox recording is in the public domain. Recording by Nikki Myers of Gettysburg, Pennsylvania. To learn more about me, visit nikkisessentials.com. Chapter 7 Frying. The process of frying follows next, in natural order, to those of roasting and grilling. A little reflection will show that in frying the heat is not communicated to the food by radiation from a heated surface at some distance, but by direct contact with the heating medium, which is the hot fat commonly, but erroneously, described as boiling fat. As I am writing for intelligent readers who desire to understand the philosophy of the common processes of cookery, so as far as they are understandable, this fallacy concerning boiling fat should be pushed aside at once. Generally speaking, ordinary animal fats are not boilable under the pressure of our atmosphere. One of the constituent fatty acids of butter, butyric acid, is an exception. It boils at 314 degrees Fahrenheit. Before reaching their boiling point, i.e., the temperature at which they pass completely into the state of vapor, their constituents are more or less dissociated or separated by the repulsive agency of the heat, new compounds being in many cases formed by recombinations of their elements. When water is heated to 212 degrees, it is converted completely into a gas, which gas, on cooling below 212 degrees, returns to the fluid state without any loss. In like manner, if we raise an essential oil, such as turpentine, to 320 degrees, or oil of peppermint to 340 degrees, or orange peel oil to 345 degrees, or patchouli to 489 degrees, and other such oils to certain other temperatures, they pass into a state of vapor, and these vapors, when cooled, recondense into their original form of liquid oil without alteration. Hence they are called volatile oils. While the greasy oils, which cannot thus be distilled, in which class animal fats are included, are called fixed oils. A very simple practical means of distinguishing these is the following. Make a spot of the oil to be tested on clean blotting paper. Heat this by holding it above a spirit lamp flame or by toasting it before a fire. If the oil is volatile, the spot disappears. If fixed, it remains as a spot of grease until the heat is raised high enough to char the paper, of which charring, a result of the dissociation above named, the oil partakes. But the practical cook may say, "This is wrong, for the fat in my frying pan does not boil. I see it boil, and I hear it boil." The reply to this is that the lard, or dripping, or butter that you put into your frying pan is oil mixed with water, and that it is not the oil but the water that you see boiling. To prove this, take some fresh lard, as usually supplied, and heat it in any convenient vessel, raising the temperature gradually. Presently it will begin to splutter. If you try it with a thermometer, you will find that the spluttering point agrees with the boiling point of water, and if you use a retort, you may condense and collect the splutter matter, and prove it to be water. So long as the spluttering continues, the temperature of the melted fat, i.e., the oil, remains about the same, the water vapor carrying away the heat. When all the water is driven off, the liquid becomes quiescent, in spite of its temperature rising from 212 degrees to above 400 degrees, when a pungent, smoky vapor comes off and the oil grows darker. This vapor is not vapor of lard, but vapor of separated and recombined constituents of the lard, which is now suffering dissociation, the volatile products passing off, while the non-volatile carbon, i.e., lard charcoal, remains behind, coloring the liquid. If the heating be continued, a residuum of this carbon in the form of soft coke or charcoal will be all that remains in the heated vessel. We may now understand what happens when something humid, say a sole, is put into a frying pan but contains fat heated above 212 degrees. Water, when suddenly heated above its boiling point, is a powerful explosive and may be very dangerous simply because it expands to 1,728 times its original bulk when converted into steam. Steam engine boilers and the boilers of kitchen stoves sometimes explode by becoming red hot while dry, and then receiving a little water which suddenly expands to steam. The noise and spluttering that is started immediately the sole is immersed in the hot fat is due to the explosion of a multitude of small bubbles formed by the confinement of the suddenly expanding steam in the viscous fat, from which it releases itself with a certain degree of violence. It is evident that to effect this amount of erupted violence, the temperature must be considerably above the boiling point of the exploding water. If it were only just at the boiling point, the water would boil quietly. As we all know, the flavor and appearance of a boiled sole or mackerel are decidedly different from those of a fried sole or mackerel. and it is easy to understand that the different results of these cooking processes are to some extent to the difference of temperature to which the fish is subjected. It will be at once understood that my theory of the chief difference between roasted or grilled meat and boiled meat applies to fried fish. That of the flavoring juices are retained when the fish is fried, while more or less of them escape into the water when boiled. Besides this, the surface of fried fish, like that of the roasted or grilled meat, is browned. What is the nature, the chemistry of this browning? I have endeavored to find some answer to this question that I might quote with authority, but no technological or purely chemical work within my reach supplies such answer. Rumford refers to it as essential to roasting, and provides for it in the manner already described, but he goes no further into the philosophy of it than admitting its flavoring effect. I must therefore struggle with the problem in my own way as best I can. Has the gentle reader ever attempted the manufacture of hardbake or toffee or butterscotch? By mixing sugar with butter, fusing the mixture and heating further until the well-known hard brown confection is produced? I venture to call this fried sugar. If heated simply without the butter, it may be called baked sugar. The scientific name for this baked sugar is caramel. The chemical changes that take place in the browning of sugar have been more systematically studied than those which occur in the constituents of flesh when browned in the course of ordinary cookery. Believing them to be nearly analogous, I will state, as briefly as possible, the leading facts concerning sugar. Ordinary sugar is crystalline, i.e., when it passes from the liquid to the solid state, it assumes regular geometrical forms. If the solidification takes place undisturbed and slowly, the geometric crystals are large, as in sugar candy. If the water is rapidly evaporated with agitation, the crystals are small, and the whole mass is a granular aggregation of crystals, as we see in loaf sugar. If this crystalline sugar be heated to about 320 degrees Fahrenheit, it fuses, and without any change of chemical composition undergoes some sort of internal physical alteration that makes it cohere in a different fashion. The learned name for this action is allotropism, and the substance is said to be allotropic, other conditioned or dimorphic, two-shaped. Instead of being crystalline, the sugar now becomes vitreous. It solidifies as a transparent amber-colored glass-like substance, the well-known barley sugar, which differs from crystalline sugar not only in respect, but has a much lower melting point. It liquefies between 190 degrees and 212 degrees, while loaf sugar does not fuse below 320 degrees. Left to itself, vitreous sugar returns gradually to its original condition, loses transparency, and breaks up into small crystals. In doing this, it gives out the heat, which during its vitreous condition had been doing the work of breaking up its crystalline structure, and therefore was not manifested as temperature. This return to the crystalline condition is retarded by adding vinegar or mucilaginous matter to the heated sugar. Hence the confectioner's name of barley sugar, which, in one of its old-fashioned forms, was prepared by boiling down ordinary sugar in a decoction of pearl barley. The French cooks and confectioners carry on the heating of sugar through various stages bearing different technical names, one of the most remarkable of which is a splendid crimson variety largely used in fancy sweetmeats, and containing no foreign coloring matter, as commonly supposed. Though nothing is added, something is taken away, and this is some of the chemically combined water of the original sugar, in the parting with which not only a change of color occurs, but also a modification of flavor, as anybody may prove by experiment. When the temperature is gradually raised to 420 degrees, the sugar loses 2 equivalents of water and becomes caramel, a dark brown substance no longer sweet, but having a new flavor of its own. It further differs from sugar by being incapable of fermentation. The first stage of this cookery of sugar has now an archaeological interest in connection with one of the lost arts of the kitchen, viz. the spinning of sugar. Within the reach of my own recollection, no evening party could pretend to be stylish unless the supper table was decorated with a specimen of this art, a temple, a pagoda, or something of the sort done in barley sugar. These were made by raising the sugar to 320 degrees, when it is fused and became amorphous, or vitreous as already described. The cook then dipped a skewer into it. The melted vitreous sugar adhered to this, and was drawn out as a thread, which speedily solidified by cooling. While in the act of solidification it was woven into the desired form, and the skilful artist did this with wonderful rapidity. I once witnessed with childish delight the spinning of a great work of art by the Duke of Cumberland's French cook in St. James's Palace. It was a ship in full sail, the sails of edible wafer, the hull a basket work of spun sugar, and the masts of massive sugar sticks, and the rigging of delicate threads of the same. As nearly as I can remember, the whole was completed in about an hour. But to return from the high art below stairs to chemical science, the conversion of sugar into caramel is already stated, attended with a change of flavor. A kind of bitterness replaces the sweetness. This peculiar flavor, judiciously used, is a powerful adjunct to cookery, and one which is shamefully neglected in our ordinary English domestic kitchens. To test this, go to one of those Swiss restaurants originally instituted in this country by that enterprising Ticinese, the late Carlo Gatti, and which are now so numerous in London and our other large towns, called for maccheroni al sugo. Notice the rich brown gravy of the sugo. Many an English cook would use half a pound of gravy to produce the like. But the basis of this halfpennyworth or less, of what I call caramel compound, as an example of which I copy the following recipe from the household edition of Gouffé's Royal Cookery Book. Melt a half pound of butter, add 1 pound of flour, mix well, and leave on a slow fire, stirring occasionally until it becomes a light mahogany color. When cool, it may be kept in the larder ready for use. Gouffé calls this liaison au roux. The English for liaison is a thickening. It is really fried flour. Burnt onion is another form of caramel, with a special flavor superadded. Plain sugar caramel is improved by the use of a little butter, as in making toffee. Thus prepared, it is really a fried sugar, rather than a baked sugar. Beurre noir, black butter, is another of the caramelized preparations used by continental cooks. While engaged upon your macaroni, look around at the other dishes served to other customers. Instead of the pale slices of meat spread out in a little puddle of pale watery liquid that are served in English restaurants of corresponding class, you will see dainty morsels covered with rich brown gravy or surrounded by vegetables immersed in the same. The sugo is greatly varied according to the requirements by additions of stock broth, tarragon vinegar, ketchup, but burnt flour, burnt sugar, or burnt onions, or burnt something, is the basis of it all. To further test the flavoring properties of browning, take some eels cut up as usual for stewing. Divide into 2 portions. Stew one brutally. By this I mean simply in a little water, serving them with this water as a pale gravy or juice. Let the second portion be well fried, fully caramelized or browned, then stewed and served with brown gravy. Compare the result. Make a corresponding experiment with the beefsteak. Cut into 2 portions, stew one brutally in plain water. Fry the other and stew it and serve brown. Take a highly baked loaf, better one that is black outside. Scrape off the film of crust that is quite black, i.e. completely carbonized, and you will come to a rich brown layer, especially if you operate upon the bottom crust. Slice off a thin shaving of this and eat it critically. Mark its high flavor as compared with the comparatively insipid crumb of the same loaf. And note especially the resemblance between this flavor and that of the caramel from sugar, and that of the browned eels and browned steak. A delicate way of detecting the flavor due to the browning of bread is to make 2 bowls of bread and milk, in the same manner, one with the crust, the other with the crumb of the same loaf. I am not suggesting these as examples of better or worse flavor, but as evidence of the fact that much flavor of some sort is generated. It may be out of place, as I think it is in the bread and milk, or it may be added with much advantage to other things, as it is by the cook who manipulates caramel and its analogues skillfully. The largest constituent of bread is starch. Excluding water, it constitutes about 3/4 of the weight of good wheaten flour. Starch differs a little from sugar in composition. It is easily converted into sugar by simply heating it with a little sulfuric acid, and by other means, of which I shall have to speak more fully hereafter, when I come to the cookery of vegetables. When simply heated, it is converted into dextrin, or British gum, largely used as a substitute for gum arabic. If the heat is continued, a change of color takes place. It grows darker and darker, until it blackens just as sugar does. The final result being nearly the same, water is driven off in both cases, but in carbonizing sugar, we start with more water. Sugar being a starch plus water, or the elements of water. Thus the brown material of bread crust or toast is nearly identical with sugar caramel. I have often amused myself by watching what occurs when toast and water is prepared, and I recommend my readers to repeat the observation. Toast a small piece of bread to blackness, and then float it on water in a glass vessel. Leave the water at rest, and direct your attention to the underside of the floating toast. Little thread-like streams of brown liquid will be seen descending in the water. This is a solution of the substance which, if I mistake not, is a sort of caramel which ultimately tinges all the water. Some years ago I commenced a course of experiments with this substance, but did not complete them. In case I should never do so, I will here communicate the results attained. I found that this starch caramel is a disinfectant, and that sugar caramel also has some disinfecting properties. I am not prepared to say that it is powerful enough to disinfect sewage, though at the same time I had a narrow escape from the Great Seal Office, where I thought of patenting it for this purpose as a non-poisonous disinfectant that may be poured into rivers in any quantity without danger. Though it may not be powerful enough for this, it has an appreciable effect on water slightly tainted with decomposing organic matter. This is a very curious fact. We do not know who invented toast and water, nor, so as far as I can learn, has any theory of its use been expounded. Yet there is extant a vague popular impression that the toast has some sort of wholesome effect on the water. I suspect that this must have been originally based on experience, probably on the experience of our forefathers or foremothers living in country places where stagnant water was a common beverage, and various devices were adopted to render it potable. Gelatin, fibrin, albumen, i.e., all the materials of animal food, as already shown, are composed, like starch and sugar, of carbon, hydrogen, and oxygen, with, in the case of these animal substances, the addition of nitrogen, but this does not prevent their partial carbonization or caramelizing, if I may invent a name to express the action which stops short of blackening. Animal fat is a hydrocarbon, which may be similarly browned, and if I am right in my generalization of all these browning processes, an important practical conclusion follows, viz. that cheap soluble caramel made by skillfully heating common sugar or flour is really, as well as apparently, as valuable an element in gravies as the far more expensive coloring matter of brown meat gravies, and that our English cooks should use it far more liberally than they usually do. The preparation of sugar caramel is easy enough. The sugar should be gradually heated till it assumes a rich brown color and has lost its original sweetness if carried just far enough. The result is easily soluble in hot water, and the solution may be kept for a long time, as it is by cooks who understand its merits. The connection with the idea of its disinfecting action, I may refer to the cookery of tainted meat or high game. A hare that is repulsively advanced when raw may, by much roasting and browning, become quite wholesome, and such is commonly the case in the ordinary cooking of hares, if it were boiled or merely stewed without preliminary browning. In this condition it would be quite disgusting to ordinary palates. A leg of mutton for roasting should be hung until it begins to become odorous. For boiling it should be as fresh as possible. This should be especially remembered now that we have so much frozen meat imported from the antipodes. When duly thawed, it is in splendid condition for roasting, but is not usually so satisfactory when boiled. I may here mention incidentally that such meat is sometimes unjustly condemned on account of its displaying a raw center when cooked. This arises from imperfect thawing. The heat required to thaw a given weight of ice and bring it up to 60 degrees is about the same as is demanded for the cookery of an equal quantity of meat, and therefore while the thawed portion of the meat is being cooked, the frozen portion is but just thawed, and remains quite raw. A much longer time is demanded for thawing, i.e. supplying 142 degrees of latent heat, than might be supposed. To ascertain whether the thawing is completed, drive an iron skewer through the thickest part of the joint. If there is a core of ice within, it will be distinctly felt by its resistance. A correspondent asks me, which is the most nutritious, a slice of English beef in its own gravy, or the browned morsel as served in an Italian restaurant with the caramel addition to the gravy? This is a very fair question and not difficult to answer. If both are equally cooked, neither overdone nor underdone, they must contain weight for weight exactly the same constituents in equally digestible form, so far as chemical composition is concerned. Whether they will actually be digested with equal facility or assimilated with equal completeness depends upon something else not measurable by chemical analysis, viz. the relish with which they are respectively eaten. To some persons the undisguised fleshiness of the English slice, especially if underdone, is very repugnant. To these the corresponding morsel, cooked according to Gouffé rather than Mrs. Beeton, would be more nutritious. To the carnivorous John Bull, who regards such dishes as nasty French messes of questionable composition, the slice of unmistakable ox flesh from a visible joint would obtain all the advantages of appreciative mastication, and that sympathy between the brain and the stomach, which is so powerful that when discordantly exerted, it may produce the effects that are recorded in the case of the sporting traveler who was invited by a Red Indian chief to a dog fight, and ate with relish the savory dishes at what he supposed to be a preliminary banquet. Digestion was tranquilly and healthfully proceeding under the soothing influence of the calumet, when he asked the chief when the fight would commence. On being told that it was over, and that in the final ragout he had praised so highly, the last puppy dog possessed by the tribe had been cooked in his honor. The normal course of digestion of the honored guest was completely reversed. Before leaving the subject of caramel, I should say a few words about French coffee, or coffee as in France, of which we hear so much. There are two secrets upon which depend the excellence of our neighbors in the production of this beverage. First, economy in using the water. Second, flavoring with caramel. As regards the first, it appears that English housewives have been demoralized by the habitual use of tea, and applied to the infusion of coffee the popular formula for that of tea, a spoonful for each person and one for the pot. The French after-dinner coffee cup has about 1/3 of the liquid capacity of a full-sized English breakfast cup, but the quantity of solid coffee supplied to each cupful is more than equal to that ordinarily allowed for the larger English measure of water. Besides this, the coffee is commonly, though not universally, flavored with a specially and skillfully prepared caramel, instead of the chicory so largely used in England. Much of the so-called French coffee now sold by our grocers in tins is caramel flavored with coffee rather than coffee flavored with caramel. And many shrewd English housewives have discovered that by mixing the cheapest of these French coffees with an equal quantity of pure coffee they obtain a better result than with the common domestic measure of 3 parts coffee and 1 of chicory. A few months ago, a sample of coffee finings was sent to me for chemical examination, that I might certify to its composition and wholesomeness. I described it in my report as a caramel, with a peculiar rich aroma and flavor, evidently due to the vegetable juices or extractive matter naturally united with the saccharine substance from which it is prepared. I have no definite information of the exact nature of this saccharine substance, but have since learned that it was a by-product of sugar refining. Neither the juice of the beetroot nor the sap of the sugar cane consists entirely of pure sugar dissolved in pure water. They both contain other constituents common to vegetable juices, and some peculiar to themselves. These mucilaginous matters, when roughly separated, carry down with them some sugar, and form a sort of coarse sweetwort, capable by skillful treatment of producing a rich caramel well suited for mixing with coffee. Returning to the subject of frying, we encounter a good illustration of the practical importance of sound theory. A great deal of fish and other kinds of food is badly and wastefully cooked in consequence of the prevalence of a false theory of frying. It is evident that many domestic cooks, not hotel or restaurant cooks, have a vague idea that the metal plate forming the bottom of the frying pan should directly convey the heat of the fire to the fried substance, and that the bit of butter or lard or dripping put into the pan is used to prevent the fish from sticking to it, or to add to the richness of the fish by smearing its surface. The theory which I have propounded above is that the melted fat cooks by convection of heat, just as water does in the so-called boiling of meat. If this is correct, it is evident that the fish should be completely immersed in a bath of melted fat or oil, and that the turning over demanded by the greased plate theory is unnecessary. Well-educated cooks understand this distinctly, and use a deeper vessel than our common frying pan. Charge this with a quantity of fat sufficient to cover the fish, which is simply laid upon a wire support, or frying basket, and left until the browning of its surface, or of the flour or bread crumbs, which it is coated, indicates the sufficiency of the cookery. The illustration is from Gouffé's excellent cookery book already quoted, and is introduced because I have found it so little understood by English housewives. Frying kettles may now be purchased at all our best English ironmongers, though until recently they were difficult to obtain. My lectures and papers have largely extended the demand and consequent supply. At first sight, the deep fat bath appears extravagant, as compared with the practice of greasing the bottom of the pan with a little dab of fat, but any housewife who will apply to the frying of sprats, herrings, the method of quantitative inductive research, described and advocated by Lord Bacon in his Novum Organum Scientiarum, may prove the contrary. Must I read the Novum Organum and buy another dictionary in order to translate all this? She may exclaim in despair. No, is my reply. This Baconian inductive method, to which we are indebted for all the triumphs of modern science, is nothing more nor less than the systematic and orderly application of common sense and definite measurement to practical questions. In this case, it may be applied simply by frying a weighed quantity of any kind of fish or cutlet in a weighed quantity of fat used as a bath, then weighing the fat that remains and subtracting the latter weight from the first, to determine the quantity consumed. If frying be properly performed, and this quantity compared with that which is consumed by the method of merely greasing the pan bottom, the bath frying will be proved to be more economical as well as the more efficient method. The reason of this is simply that much or all of the fat is burnt and wasted when only a thin film is spread on the bottom of the pan, while no such waste occurs when the bath of fat is properly used. The temperature at which the dissociation of fat commences is below that required for delicately browning the surface of the fish itself, or of the flour or breadcrumbs, and therefore no fat is burnt away from the bath, as it is by the overheated portions of a merely greased frying pan. And as regards the quantity adhering to the fish itself, this may be reduced to a minimum by withdrawing it from the bath when the whole is uniformly at the maximum cooking temperature, and allowing the fluid of the fat to drain off at once. It may be supposed that by a complete immersion of the fish in the fat bath, and more fat will soak into it, but such is not the case. The water amidst the fibers of the fish is boiling and driving out steam so rapidly that no fat can enter if the heat is well maintained to the last moment, and the frying not continued too long. When cooked on the greased plate, one side is necessarily cooling, and the fat settling down into the fish to occupy the pores left vacuous by the condensing steam, while the other is being heated from below. The temperature of the fat bath may be tested by the ordinary cook's method, that of throwing into it a small piece of breadcrumb about the size of a nut. If it frizzles and produces large bubbles of steam, the temperature of frying in the hottest of fat is reached. If it frizzles slightly and only gives out small steam bubbles, you have the temperature demanded for slow frying. The bath frying demands separate supplies of fat, one for fish, another for cutlets and other similar kinds of meat, a third for such goody-goodies as apple fritters, a most wholesome and delicious dish, too rarely seen on English tables. I suspect that the prevalence of the greased frying pan is the reason of its rarity. Cooked by this barbaric device, apples are scarcely eatable, but when thin slices are immersed in a bath of melted fat, at a temperature of about 300 degrees Fahrenheit, the water of their juice is suddenly boiled, and as this water is contained in a multitude of little bladder-like cells, they burst, and the whole structure is puffed out to a most delicate lightness, far more suitable for following solid meats than soddened fruit enveloped in heavy, indigestible pudding paste. Another advantage is that with proper apparatus, wire basket, kettle, and store of special fat, the fritters can be prepared and cooked in about 1/10 of the time demanded for the preparation and cookery of an apple pudding or pie. A few seconds of immersion in the fat bath is sufficient. The fat used in frying requires occasional purification. I may illustrate the principle on which it should be conducted by describing the method adopted by refining of mineral oils, such as petroleum or the paraffin distillates of bituminous shales. These are dark, tarry liquids of treacle-like consistency with a strong and offensive odor. Nevertheless, they are, at but little cost, converted into the crystal oil used for lamps. And that beautiful pearly substance, the solid, translucent paraffin, now so largely used in the manufacture of candles. Besides these, we obtain from the same dirty source an intermediate substance, the well-known vaseline, now becoming the basis of most of the ointments of the pharmacopoeia. This purification is effected by agitation with sulphuric acid, which partly carbonizes and partly combines with the impurities and separates them in the form of a foul and acrid black mess, known technically as acid tar. When I was engaged in the distillation of cannel and shale in Flintshire, this acid tar was a terrible bugbear. It found its way mysteriously into the Allan River and poisoned the trout, but now, if I am correctly informed, the Scotch manufacturers have turned it to profitable account. Animal fat and vegetable oils are similarly purified. Very objectionable refuse fat of various kinds is thus made into tallow, or material for the soap maker, and grease for lubricating machinery. Unsavory stories have been told about the manufacture of butter from Thames mud, or the nodules of fat that are gathered therefrom by the mudlarks, but they are all false. See paper on the oleaginous product of Thames mud in Science in Short Chapters. It may be possible to purify fatty matter from the foulest of admixtures, and do this so completely as to produce a soft, tasteless fat, i.e., a butter substitute. But such a curiosity would cost more than half a crown per pound, and therefore the market is safe, especially as the degree of purification required for soap making and machinery grease costs but little, and the demand for such fat is very great. These methods of purification are not available in the kitchen, as oil of vitriol is a vicious compound. During the siege of Paris, some of the academicians devoted themselves very earnestly to the subject of the purification of fat in order to produce what they termed siege butter, from the refuse of slaughterhouses, and edible salad oils and crude colza oil, from the rancid fish oils used by the leather dresser. Those who are specially interested in the subject may find some curious papers in the Comptes Rendus of that period. In volume 71, page 36, M. Boyot describes his method of mixing kitchen stuff and other refuse fat with lime water, agitating the mixture when heated, and then neutralizing with an acid. The product thus obtained is described as admirably adapted for culinary operations, and the method is applicable to the purpose here under consideration. Further on the same volume is a note on suets and alimentary fats by M. Dubrunfaut, who tells us that the most tainted of alimentary fats and rancid oils may be deprived of their bad odors by appropriate frying. His method is to raise the temperature of the fat to 140 degrees to 150 degrees centigrade, 284 degrees to 302 degrees Fahrenheit, in a frying pan, then cautiously sprinkle upon it small quantities of water. The steam carries off the volatile fatty acids which produce the rancidity in such as fish oils, and also removes the neutral offensive fatty matters that are decomposable by heat. In another paper by M. Fouet, this method is applied to the removal of cellular tissue of crude fats from slaughterhouses. It is really nothing more than the old farmhouse proceeding of rendering lard by frying the membranous fat until the membranous matter is browned and aggregated into small nodules, which constitute the scratchings, a delicacy greatly relished by our British ploughboys at pig-killing time, but rather too rich in pork fat to supply a suitable meal for people of sedentary vocations. The action of heat thus applied and long continued is similar to that of the strong sulphuric acid. The impurities of the fat are organic matters more easily decomposable than the fat itself, or otherwise stated. They are dissociated into carbon and water at about 300 degrees Fahrenheit, which is a lower temperature than that required for the dissociation of the pure oil or fat. By maintaining this temperature, the compounds become first caramelized, then carbonized nearly to blackness, when all their powers of offensiveness vanish. In the more violent factory process of purification by sulphuric acid, the similar action which occurs is due to the powerful affinity of this acid for water. This may be strikingly shown by adding to thick syrup or pounded sugar about its own bulk of oil of vitriol, when a marvelous commotion occurs, and a magnified black cinder is produced by the separation of the water from the sugar. The following simple practical formula may be reduced from these data. When considerable quantity of much used frying fat is accumulated, heat it to about 300 degrees Fahrenheit as indicated by the crackling of water when sprinkled on it. Better still, by a properly constructed thermometer. Then pour the melted fat on hot water. This must be done carefully, as a large quantity of the fat at 300 degrees poured onto a small quantity of boiling water will illustrate the fact that water when suddenly heated is an explosive compound. The quantity of water should exceed that of the fat, and pouring be done gradually. Then agitate the fat and water together, and, if the operator is sufficiently skillful and intelligent, the purification may be carried further by carefully boiling the water under the fat and allowing its steam to pass through. But this is a little dangerous, on account of the possibility of what the practical chemist calls bumping, or the sudden formation of a big bubble of steam that would kick a good deal of the superabundant fat into the fire. Whether this supplementary boiling is carried out or not, the fat and the water should be left together to cool gradually, when a dark layer of carbonized impurities will be found resting on the surface of the water and adhering to the bottom of the cake of fat. This may be peeled off and put into the waste grease pot, to be further refined with the next operation. Ultimately, the worst of it will sink to the bottom of the water. A careful cook may keep the supply of frying fat continually good by simply pouring it into a basin. A deep pudding basin with a small area at the bottom is best, letting it solidify there, and then paring away the bottom sediment. Even this dirty-looking sediment need not be altogether wasted. When a considerable quantity has accumulated, it may be purified by the method of Dubrunfaut and Fouet above described. As ordinary thermometers register but little above 212 degrees, and laboratory thermometers are too delicately constructed for kitchen use, I requested Messrs. David and Company to construct a special thermometer for testing the temperature of heated fat. They have accordingly made an instrument that answers the purpose very well. It is like a laboratory thermometer, i.e., a glass tube with a long bulb, and the degrees engraved on the glass itself, but but the bulb is turned at right angles to the tube, so that it is horizontal when the tube stands perpendicular and lies under a stand just above the level of the bottom of the kettle. The instrument thus stands alone firmly, with its bulb fully immersed even in a very shallow bath of fat. Gouffet says fat is the best for frying, the light-colored dripping of roast meat, and the fat taken off broth are to be preferred. These failing, beef suet, chopped fine and melted down with a slow fire, without browning, will do very well. When the bottom of the stewpan can be seen through the suet, it is sufficiently melted. He is no advocate for lard, as it always leaves an unpleasant coating of fat on whatever is fried in it. Olive oil of the best quality is almost absolutely tasteless, and having as high a boiling point as animal fats, it is the best of all frying media. In this country there is a prejudice against the use of such oil. I have noticed at some of those humble but most useful establishments, where poor people are supplied with a penny or 2-penny portions of well-cooked, good fish, that in the front is an inscription stating, only the best beef dripping is used in this establishment. This means a repudiation of oil. On my first visit to Arctic Norway, I arrived before the garnering and exportation of the spring cod harvest was completed. The packet stopped at a score or so of stations on the Lofoten's and the mainland. Foggy weather was no impediment, as an experienced pilot free from catarrh could steer direct to the harbor by following his nose. Huge cauldrons stood by the shore in which were stewing the last batches of the livers of codfish caught a month before and exposed, in the meantime, to continuous Arctic sunshine. Their condition must be imagined, as I abstain from description of details. The business then proceeding was the extraction of oil from these livers. It is, of course, cod liver oil, but is known commercially as fish oil or cod oil. That which is sold by our druggists as cod liver oil is described in Norway as medicine oil, and though prepared from the same raw material, is extracted in a different manner. Only fresh livers are used for this, and the best quality, the cold-drawn oil, is obtained by pressing the livers without stewing. Those who are unfortunately familiar with this carefully prepared, highly refined product know that the fishy flavor clings to it so pertinaciously that all attempts to completely remove it without decomposing the oil have failed. This being the case, it is easily understood that the fish oil stewed so crudely out of the putrid or semi-putrid livers must be nauseous indeed. It is nevertheless used by some of the fish fryers, and refuse Gallipoli, olive oil of the worst quality, is sold for this purpose. The oil obtained in the course of salting sardines, herrings, is also used. Such being the case, it is not surprising that the use of oil for frying should, like the oil itself, be in bad odor. I dwell upon this because we are probably on what, if a fine writer, I should call the eve of great revolution in respect to frying media. 2 new materials, pure, tasteless, and so cheap as to be capable of pushing pig-fat lard out of the market, have recently been introduced. These are cottonseed oil and poppyseed oil. The first has been for some time in the market offered for sale under various fictitious names, which I will not reveal, as I refuse to become a medium for the advertisement of anything, however good in itself, that is sold under false pretenses. As a bale of cotton yields half a ton of seed, and every ton of seed may be made to yield 28 pounds to 32 pounds of crude oil, the available quantity is very great. At present only a small quantity is made, the surplus seed being used as manure. Its fertilizing value would not be diminished by removing the oil, which is only a hydrocarbon, i.e., material supplied by air and water. All the fertilizing constituents of the seed are left behind in the oil cake from which the oil has been pressed. Hitherto cottonseed oil has fallen among thieves. It is used as an adulterant of olive oil. Sardines and pilchards are packed in it. The sardine trade has declined lately. Some say from deficient supplies of the fish. I suspect that there has been a decline in the demand due to the substitution of this oil for that of the olive. Many people who formerly enjoyed sardines no longer care for them, and they do not know why. The substitution of cottonseed oil explains this in most cases. It is not rancid, but has no decided flavor, but still is unpleasant when eaten raw, as with salads or sardines. It has a flat, cold character, and an aftertaste that is faintly suggestive of castor oil, but faint as it is, it interferes with the demand for a purely luxurious article of food. This delicate defect is quite inappreciable in the results of its use as a frying medium. The very best lard or ordinary kitchen butter, eaten cold, has a more objectionable flavor than refined cottonseed oil. I have not tasted poppyseed oil, but I am told that it is similar to that from the cottonseed. As regards to the quantities available, some idea may be formed by plucking a ripe head from a garden poppy and shaking out the little round seeds through the windows on the top. Those who have not tried this will be astonished at the numbers produced by each flower. As poppies are largely cultivated for the production of opium, and the yield of the drug itself by each plant is very small, the supplies of oil may be considerable. 571,542 hundredweight of seeds were exported from India last year, of which 346,031 hundredweight went to France. Palm oil, though at present practically unknown in the kitchen, may easily become an esteemed material for the frying kettle. At present, the familiar uses of palm oil in candle making and for railway grease will cause my suggestion to shock the nerves of many delicate people, but these should remember that before palm oil was imported at all, the material from which candles and soap were made, and by which cartwheels and heavy machinery were greased, was tallow, i.e. the fat of mutton and beef. The reason why our grandmothers did not use candles for frying when short of dripping or suet was that the mutton fat constituting the candle was impure. So are the yellow candles and yellow grease in the axle boxes of the railway carriages. This vegetable fat is quite as inoffensive in itself, quite as wholesome, and sentimentally regarded less objectionable than the fat obtained from the carcass of a slaughtered animal. When common sense and true sentiment supplant mere unreasoning prejudice, vegetable oils and vegetable fats will largely supplant those of animal origin in every element of our dietary. We are but just beginning to understand them. Chevreul, who is the first to teach us the chemistry of fats, is still living, and we are only learning how to make butter, not inferior Dorset, but choice Normandy, without the aid of dairy produce. There is, therefore, good reason for anticipating the inexhaustible supplies of oil obtainable from the vegetable world, especially the tropical vegetation, will ere long be freely available for kitchen uses, and the now popular product of the Chicago hog factories will be altogether banished therefrom, and used only for greasing cartwheels and other machinery. As a practical conclusion of this part of my subject, I will quote from the Oil Trade Review of this month, December 1884, the current wholesale prices of some of the oils possibly available for frying purposes. Olive oil from 43 pounds to 90 pounds per ton of 252 gallons. Cod oil, 36 pounds per ton. Sardine or train, i.e. the oil that drains from the pilchards, herrings, sardines, when salted, 27 pounds 10 shillings to 28 pounds per ton. Coconut, from 35 pounds to 38 pounds per ton of 20 hundredweight. This, in the case of oil, is nearly the same as the measured ton. Palm, from 38 pounds to 40 pounds 10 shillings per ton. Palm nut or copra, 31 pounds 10 shillings per ton. Refined cottonseed oil, 30 pounds 10 shillings to 31 pounds per ton. Lard, 53 pounds to 55 pounds per ton. The above are the extreme ranges of each class. I have not copied the technical names and prices of the intermediate varieties. 1 penny per ton is equal to 9 pounds 6 shillings. 8 pence per ton, or in round numbers, 1 pound per ton may be reckoned as 1/9 of a penny per pound. Thus the present price of best refined cottonseed oil is 3½ pence per pound. Of coconut oil, 3 3/4 pence. Palm oil from 3½ pence to 4½ pence, while lard costs 6 pence per pound wholesale. I should add in reference to the seed oils that there is a possible objection to their use as frying media. Oil extracted from seeds contains more or less lanolin, so named from its abundance in linseed oil, which when exposed to air combines with oxygen, swells, and dries. If the oil from cottonseed or poppy seed contains too much of this, it will thicken inconveniently when kept for a length of time exposed to air. Palm oil is practically free from it, but I am doubtful respecting palm nut oil, as most of the nut oils are dryers. Extravagant cooks delude confiding mistresses by demanding butter for ordinary frying. A veneration for costliness is one of the vulgar vices, especially dominant below stairs. In many cases a worse motive induces the denunciation of the dripping and skimmed fat recommended by Gouffé as above, and the substitution of lard or butter for it. This is the practice of selling the dripping as kitchen stuff. End of Chapter 7. Recording by Nikki Myers from Gettysburg, Pennsylvania. To learn more about me, visit www.nickysessentials.com.